Hello, everybody. This is Sunday. It's March 12th, and we are headed into week 9 of our online astronomy course. Module 9 is about the sun, our star. This is the start of our study of stars, their lives, their evolution, their deaths, and how they are arranged in galaxies and how galaxies are arranged in the universe. So that's a look ahead, but we're starting out with the sun. Now, before I talk about that, I do have a piece of astronomy news that I think is pretty cool. And so I'll just share the screen here. And this is the discovery of a new comet. Now, the last comet was really a disappointment. It didn't get very spectacular at all. But this one, they are really forecasting a great display. And you'll have to wait until 2024. And in October of 2024, it will be closest to Earth. So just put that on your mental calendar. It's one more thing that is going to be great going on in the sky. But the greatest thing, of course, is going to be a total solar eclipse next year. And it won't be visible everywhere in the U.S. There's just a tiny band reaching across the U.S. It goes from Texas and then up north from there. But if you have not seen a total solar eclipse, I would do whatever you have to do to get into that band and see it when it happens. But so 2024 is going to be a good year for astronomy. I do have to remind you that we do have an exam this coming week. It's exam number 3. It's right between modules 8 and 9 on your module page. It covers modules 5, 6, 7, and 8. Same format, 35 multiple choice questions. You can take it twice if you want to. And so I'll remember today to send out an email to everybody, also reminding them of this. The exam opens tomorrow, Monday, on March 13th, and it's going to close on next Sunday, March 19th. So make sure and take that, and I hope you have good luck with that. Now, let's start talking about the sun. The sun is our star. What is the sun? What is the sun like? Does it have a solid surface? If you look at pictures of the sun, it looks like a big ball. And so you might think, oh, it has a surface, but not at all. The sun is totally gaseous all the way through. It's 71% of its mass is hydrogen. And about helium is about 27%. 27% of its mass is helium. And then that leaves about 2% for other stuff, other elements like we're made of. So the sun is not made of the same stuff that Earth is, except really, really hot. No, the sun is an entirely beast, and it is entirely gaseous all the way through. And in fact, before you get in very far to the sun, you find out that these atoms of hydrogen and helium and other stuff, those atoms, because the sun is so hot, the atoms are colliding around so vigorously that the atoms become ionized. And so as you travel down into the sun, what you run into are simply the bare nuclei of atoms. Now, what happens to the electrons? They're still floating around there, but they're just not attached to the nucleus. So, how big is the sun? I say a big ball of gas. Uh, for instance, here's the Earth, and you can compare the size of Earth to the curvature of the sun. If I were to hollow out the sun and start dropping in planet Earths one at a time, I could put in over 1 million Earths within the space that's taken up by our sun. Just incredible. And also, how bright is the sun? You know, it's blinding to look at. But what is the sun's luminosity? The luminosity of the sun is the amount of energy, amount of light energy that is given off per second by the sun. Now, our sun gives off 4 times 10 to the 26 watts of light every second. And it streams from there out into space. And that is equivalent to 4 million 100-watt light bulbs. So the sun is just tremendously bright, a tremendous source of energy, and all of the energy on Earth, except for nuclear energy, ultimately derives from the sun's energy. You know, fossil fuels. Millions of years ago, there were swamps and ferns and trees growing in the swamps. Those decayed, were compressed into coal, and now we're using that. But where did those plants come from? They use the sun's energy for photosynthesis. So, and dams, well, that's the power of evaporation. The sun's rays strike, say, an ocean, evaporates some water, that water drifts over a reservoir, it rains, and then that water runs out of the reservoir through a power plant, and that flowing water turns a turbine, and that converts the energy of that flowing water into electrical energy. Oh, but what was the original source of the water's energy? It was the sun. So we are very lucky that we live just the right distance from the sun, that it's capable of sustaining life and is responsible for much of what's going on the surface of the Earth and in its atmosphere. Well, where does the sun get all that energy? You know, this used to be a really big puzzle. People thought, well, you know, if maybe it's like coal burning or wood burning, but they knew how big the sun was. They knew its mass, just using Kepler's laws. And they figured out that wood can only burn for maybe 800,000 years. And clearly we've been around a lot longer than that, even back then. And they thought, well, maybe, you know, as the sun is, as I said, just a big ball of gas, and as it slowly collapses, the idea went, as it slowly collapses, it can convert that gravitational energy, that compression, into the energy of light. No. In the first place, the sun is not collapsing to any great extent. It's in equilibrium, we'll find out, that the pressure inside exactly balances the downward pull of gravity. So pressure on the inside pushes out, gravity pulls down, and the sun is nice and stable. Well, what could it be? And it wasn't until the 1930s that a scientist and astronomer named Hans Bethe figured out what powers the sun and other stars. And the idea here is that the sun is made of hydrogen. And as you move inwards, the layers on top of the sun compress the material underneath. So inside the sun, the gas is very dense and it's very hot. And under those conditions, in just the central regions of the star, you can have nuclear fusion going on. Fusion because you have lighter elements fusing into heavier elements. And in this case, the lighter element is hydrogen. So hydrogen goes into this equation. And then what comes out? Helium. Now, you might know that, hydrogen nucleus, and remember, these are just bare nuclei down there. The electrons have been removed from the atoms. So hydrogen nucleus is just a proton. But the helium nucleus has 4 times as many particles. It has 2 protons and 2 neutrons. And so what I need is 4 protons to fuse together to form 1 helium nucleus. And that is that 4 protons come in, they fuse together, and 1 helium nucleus comes out. In fact, this is called the proton-proton chain because it is 4 protons coming together. Now, they don't come together all at once. There's a chain of reactions that assembles a helium nucleus out of 4 protons. And that's what Beta was able to figure out. And that explains why the sun is shining. It's just amazing to realize that so much energy is being liberated. In fact, in 1 second, the sun gives off enough energy to power Earth's energy needs for 800,000 years. Now, of course, seen from the sun, the Earth is just a little dot. And so most of that energy just streams out into space and it never reaches Earth so we can utilize it. Now, I can also tell you that what's going on, how much, when I say that, I told you how 4 protons comes together to form a helium nucleus, but it doesn't tell you where the energy comes from. And that's really pretty cool. What happens is that, let's suppose that there are 1,000 kilograms of protons coming into this reaction. And they fuse, they form together to form our 1 helium nucleus. So if 1,000 kilograms comes in and fuses, only 993 kilograms of helium comes out. There's 7 missing. So where did that missing mass go? And the answer is it goes into E equals mc squared. What happens is that missing mass is completely converted into energy. So the sun is actually, using up hydrogen, producing helium. And in that process, some mass is lost. About 4 million tons of mass every second, converted from hydrogen into helium. But the sun is so massive, it has enough hydrogen for these reactions to go on for about another 5 billion years. The sun is about halfway through its lifetime. It's 4.6 billion years old, and It can keep on going for about another 5 billion years. Now, it's natural to wonder what comes next. And that is the story of coming modules, the story of stellar evolution. Well, that those photons of light that are released, those are very high energy particles. But inside the sun is so dense that the photons travel about a centimeter. And then bonk, they bounce off and go a different direction. And bonk, in a different direction, different direction, different direction. And so they wander their way out of the sun. And on average, it takes about 1 million years for the light created in the sun's center to reach the surface. So when you go out, look up at the sun, and feel that sunlight hitting your face, you're looking at light that was created around 1 million years ago in the center of the sun. What else can I tell you? Well, take a look at this picture. You're hiding behind me. Maybe I'll go the other way. You can see it a little bit better. Hiding behind me here is a huge, big looping flare. And this is where gaseous particles are shot up into the sun's atmosphere, and they are captured by the magnetic field of the sun, and they loop up and around and down again. So they're constrained by the magnetic field of the sun. This happens in the hottest part of the sun's atmosphere, called the corona, is where you see all these big streamers. And below the corona, there's another narrower part of the atmosphere called the chromosphere, a sphere of color. And that's glowing red because of the ionized hydrogen, like the pink you saw in the glowing gas tubes we looked at in the video. And finally, there's a photosphere, which is another way of saying the visible surface of the sun. But you might think, oh, that's great, that these loops of gas are trapped in the magnetic field of the sun. What if they ever hit the Earth? And the answer is they can, because you can have holes in the sun's corona, that outermost part of the atmosphere. And you can have streams of particles shot out and going toward us here on Earth. It can cause our electrical grid system to have troubles. It can knock out communication satellites. It can do all sorts of damage. And so we are regularly watching the sun for these coronal mass ejections, as they're called, CMEs, coronal mass ejection. On the other hand, they do cause pretty displays here on Earth. If these particles get caught in Earth's magnetic field, they spiral in toward the polar regions, because that's where the magnetic field of Earth enters the Earth. And when they hit Earth's atmosphere, the atmosphere glows, and that's what an aurora is. And so if you've ever seen an aurora, and I've seen one once in Ogden, but I haven't seen really a good display. But if you've ever seen these shimmering curtains of green or violet or whatever color it is, depending upon how high those particles hit Earth's atmosphere and what is in the atmosphere at that level, it's just a wonderful display. Finally, let's take a quick look at stellarium. So I'm going to pull up stellarium here. There we go. And so here's stellarium. And you might say, what in the world is this? Well, we are looking toward the south, and you might notice if you look at the stars, here is Orion, here is Sirius, the brightest star in the sky. And so this is the same view we've seen a lot this semester, looking out there. But before, I've always shown you the Western constellations, the constellation as envisioned by the American Astronomical Union, I'm sorry. But I'm sorry, the International Astronomical Union, IAU. But other cultures have other pictures, other stories that they tell, and they see those patterns in the sky that remind them of how that story's told. And this is an old Hindu representation of the night sky. You can see it's quite different. I'll just call your attention down here to Sirius, the dog star in Canis Major. And it is pictured as a hunter with a bow and arrow. And up here, Orion, instead of being the hunter, this is the skull of a deer with an arrow through its head. So different cultures have different symbols in the sky. And I'll just go back to the Western sky culture. You can change these yourself in Stellarium. There's all sorts of ones to look through. But need to go back to Western. Oh, it's hiding. There we go. There's Western. And there they are, just as we have envisioned them, with Sirius, Canis Major, the big dog, and the hunter up here for Betelgeuse. And I will point out one thing. We're looking south here. We're looking south on the 14th. That would be Tuesday at around 9 o'clock. Daylight savings time has hit, so we have to go out later to have the same view of the sky. And you might notice that earlier in the semester that Orion is much further to the east. But now as Earth goes around the sun, Betelgeuse is marching to the west. And soon the sun will pass in front of Orion and Betelgeuse, and we won't be able to see them anymore until the following fall. Well, that is about it. I will remind you that there's one cool video that of the sun that I have posted, and it is a picture taken of the sun every day for 10 years. And if you watch that video, and I hope you will, it's really pretty cool. So I will leave you with that just for a few seconds here at the very end. And I hope I'll see you next time. So until then, bye-bye.